Today I'd like to go over the second half of Chapter 8, which is the geometric distribution. The geometric distribution has some similarities to the binomial distribution, but there's also some differences. So here's some examples I've got. In the case of the binomial distribution, we knew how many trials we were going to have. The number of trials was predetermined. However, sometimes we want to know how many trials will it take before something happens. For example, we want to play a game until we win, or maybe until we lose. We want to roll a die or a pair of dice until we get an 11. Maybe the mechanic is waiting for the first plane to arrive at the airport that needs repairs, or a basketball player continues to shoot baskets until he makes it. These situations all fall under the geometric distribution. So let's look at four characteristics of the geometric distribution. These are very similar to the ones that we had for a binomial distribution. Each event will fall into one of two categories, the success or failure. The probability of success remains the same each time. The observations are all independent, but instead of having a fixed number of observations, with the geometric distribution, the variable of interest, or x, is the number of trials it takes to obtain the first success. Now we'll recall that a success could be a good thing or a bad thing. So again, it could be shooting baskets until you finally miss one, or it could be shooting baskets until you finally make one. It just depends on how you define what a success is. So now let's go through each of these three cases. Are the following situations geometric? Why or why not? And what would you need to assume in order to make them geometric? Number one, a hunter hunts until he gets a deer. So is there a success or a failure? Sure. Is there a fixed number of observations? Well, I don't know about a fixed number of observations. What is an observation? Maybe you could say each day. So if we had a fixed number of observations, fiddle. Well, I don't know how to go back and do this. I got to talking about binomials, so let me talk about geometric. Don't need a fixed number of observations. We need to do it until we get the success. But what is an observation? That's what I need to worry about. It would need to be, say, a day. The probability of success, is that the same each day? I don't know. Are the days independent? I don't know. If I assume the days are independent, the probability of success stayed the same, in other words, the other deer weren't getting killed throughout the season, then perhaps it would be geometric. And I hunt until we get that first success. Number two, an oil company drills until it gets oil. This is similar. Is there success or not? Sure. Oil or not oil. Are the probabilities of success the same each time we drill? I don't know. Are the drills independent? I don't know. If we assumed those two things, we could make it geometric. And then we continue to do it until the success comes. That's getting oil. Number three is the most straightforward. If we define a success as flipping heads, the flips are independent. The probability of flipping heads is the same each time, and it's either heads or not heads. In this case, heads or tails. So that one would definitely be geometric. So now I'd like to look at the formulas and the math behind the way a geometric distribution works. Let's define x as the number of rolls to get a 3 on a die. So x is going to be the number of rolls it takes to get a 3 on a die. Well, this pen's kind of hard to work with. All right, so a success is a 3. The rolls are independent. The probability of success stays the same each time. And let's work through it and see how this would work. So what's the smallest number x could be? It's going to be 1. That's the smallest it could be. Now with the binomial distribution, the smallest thing x could be was 0, meaning 0 successes. But in the geometric distribution, you're going to have a success. The question is, how long does it take to get there? So what's the probability? My 3 comes on the first roll. 1/6. All right. How about the probability that my 3 comes on the second roll? Well, in this case, it wasn't the first roll, but it was the second roll. So I failed 5/6, and then I succeeded 1/6. All right, how about the third roll is my first 3. which means I failed, and then I failed, and then I succeeded. Or, condensed down, that's the probability of failing twice, and the next time I succeeded. So generically speaking, what's the probability that I finally succeed on, we'll say, the nth roll? This is the same notation the book uses. Well, what I've got to do is fail 1 minus p all but the last time, and then I succeed. So that's the generic formula for a geometric distribution. Now, some of you may ask, how come there's no binomial coefficient? Oh, wait, I know why. It's called the binomial coefficient. But if you'll recall, the whole purpose of the binomial coefficient was to list the number of ways that you could arrange the successes among all of your opportunities. So the number of ways you could arrange your 4 boys among a family of 7 kids. Well, here we know what the arrangement is. In a geometric situation, we know what the arrangement is. The arrangement is such so that the first and only success came the very last time you did it. You only have one success in a geometric distribution, because once you get that success, you quit. So all of the ones before the last time were failures. There's no way to rearrange those, because if you rearrange them and put the success somewhere else, you would have stopped then. So this is actually an infinite series. It would go on forever and ever and ever, because it could theoretically take you forever to do it. And I'll show you, before I do another problem, the formulas for mean and standard deviation. The expected value for a geometric distribution, or the mean, is 1 over p. 1 over p is the mean, and the variance is, of course, that's sigma squared. That's 1 minus p over p squared. 1 minus p over p squared. And that's the variance. Of course, the standard deviation would be the square root of that. And it's probably a good thing at this point to remind you, these formulas were different for binomial distributions. The formulas I'm giving you right now are the formulas for geometric distributions. So let's go through one more example. Let's say that I would like to play you in checkers, and I'm not very good. The probability I beat you is about 30%, but I'm persevering, and I'm going to keep playing you in checkers every day until I finally win. But I don't really get any better, so my games are all independent. That probability stays the same. What's the probability the first time I beat you is the first time we play? Of course, it's 30%. But what's the probability the first time I beat you is the second time we play? Well, it's 70% times 30%, meaning I lost the first game and I won the second one. What's the probability the first time I beat you was the third time? Well, that's 2 failures and then a success. The calculator, of course, will do these things for you. This would be the Geomet PDF, and we've got to talk about the arguments that go here. For binomial, you'll recall we did NPX. For geometric, we don't have a fixed n, so all you need are p and x, the probability of success, and the number we're interested in. So if you do that, if you do this function right here, you'll get 0.3. If you do this function, Geomet PDF 0.3 comma 2, you'll get 0.3 times 0.7. Now I could ask you, what's the probability that I beat you sometime in the first 3 tries? Well, I could simply add these 3 values up, or I could use the CDF function of 0.3, comma 3. And that would give me the same value right there as adding these three things up, just like we did before. If I'm going to continue to play, and after I beat you, I kind of forget, and we start the whole rigmarole over again, and do this repeatedly. So I play you until I win, and I count how many times it was. And then I start over, and I play you until I win, and I count how many times it was. What's the average number of times it would take before I finally beat you? Or put another way, what's the expected number of times? Well, formula is 1 over p, so it's 1 over 0.3. And to find the variance, I would use that other formula that I gave you. The variance for this would be 1 minus p over p squared. Or in other words, 1 minus 0.3 over 0.3 squared. And that formula will give you the variance on all these different times that I play you until I finally win. Finally, just as I did with the binomial distribution, I could put these things in lists in my calculator and make histograms and graph it and look at it that way. The only difference here is the geometric distribution technically goes on forever and ever and ever. It doesn't have a definite stopping point because it might take you a really long time to win. So most of the time we would just do, I don't know, the first 5 or 10 numbers in there and then show the list, and you can kind of tell how the graph would trail off. And if I looked at the CDF graph, of course, it's getting closer and closer and closer to 100% and not quite getting there until you've done it an infinite number of times. That's the geometric distribution.